So this talk is going to be a little different than what we've had in the past. It's not as focused on the science. I'm not a scientist. I do operations. So I'm talking a little bit about this program that we have that's very unique to CU, to LASP, and that's using students to help us fly satellites. And I'm also tying it into some really cool Kepler results that have been, and how Kepler works and some of the latest results. So it's a combination of both, and hopefully you'll enjoy it. This was done a few years ago. You know, your normal spacesuit, a little Star Trek-y, and then CU boulder. I think it's actually, they did this for the AIM launch. They put this cartoon out when we talked about our students involved in another program that we launched several years ago. The reason they do that is because we have such a strong involvement of students. LASP is an institute that does very cool science within the solar system. We build instruments, we're building spacecraft, and we do this thing where we operate the spacecraft and do the data processing, have the whole IT infrastructure to do all that. And we do this with undergrad students mostly, and some grad students. So we're going to be hitting, actually last year was a big anniversary for us. We started as the Upper Air Lab. We kind of evolved and went, and actually one of the interesting things is we had some engineers that were building instruments that were, that talked to the Ball brothers family and formed Ball Aerospace out of that. And so Ball Aerospace was formed out of LASP engineers. And if you follow Ball, they got out of the jar business. They're doing cans. So Ball Aerospace is the oldest part of the Ball Corporation, little known. We kind of started doing NASA work in the 50s and started building some very cool instruments, changed our name sometime in the early 60s, and we've sent an instrument to every planet in the solar system. And how do we do that? How do we do that? So we have a great group of scientists, about 70 scientists work at LASP, looking at everything from planets to the mesosphere, upper atmosphere, the sun, and space weather, solar physics. What's really cool is these scientists will walk down the hall, actually to another building now. They used to walk down the hall when we were smaller, and work with the engineers saying, how can we build an instrument that looks at the atmosphere of Mercury, which has a very little atmosphere, but it does have an atmosphere. These engineers are brilliant guys. They design the instrument, build it, test it. We have the test facilities here, put it on a rocket, launch it, get it up there, and then we take over. We do the spacecraft operations, we do payload operations. So a science instrument that's on a satellite, we operate that. We do the analysis of that science data, and then we also schedule what's going on with that instrument or that spacecraft to collect as much of that science that we can. And we do that all with students involved pretty much with every step. Probably an eye chart if you're all the way in the back, but showing all our missions that we've participated in, starting with the sun, covering all the planets, a number of rocket launches that we've had. And as I mentioned before, one of our claims to fame is that LASP has put up an instrument to every planet. And then the color coding, the orange color, is missions that we've actually operated with from LASP. So specifically, our group here, when we have a mission, such as Kepler, we actually developed and tested all the procedures, came up with the software that we needed to actually operate that mission. Worked closely with Ball Aerospace, who built the spacecraft, worked with the NASA, JPL, NASA Ames people. Then we operate that mission here, and when you leave tonight, the ops room is right outside the door. It's in another compartment. It says, don't don't wave to the animals. We have some of our animals that work in that place sitting in the audience. So those are the folks that are operating the spacecraft and the payload. And then we also process the data for most of our missions. Kepler's a little different, but we process it and distribute it to the science community. We've done a lot of missions, and we currently have 4 missions up there right now. SOURCE is a mission that's looking at the sun, at the solar irradiance from the sun. QuickScat is starting its 19th year. It's a Ball Aerospace spacecraft looking at ocean surface winds. And that one is still operating. It's still collecting science and still useful to the science community. We did have a mission called ICESat, and there's an ICESat 2 now being built that somebody else is going to operate. But that was used to study the ice sheets. AIM is a great mission, aeronomy of ice in the mesosphere. It's just easier to say AIM. Studying polar mesospheric clouds. And again, another mission going strong, continuing on in extended mission. And one I really enjoy is Kepler, and I'll talk more about that later, looking for planets. One of the things that we operate that's on the very large scale is the magnetospheric multiscale mission. This is 4 spacecraft that are flying in formation. NASA Goddard operates these spacecraft. They go in a very highly elliptical orbit. It takes about 70-some hours to go through their orbit. Each of these 4 spacecraft have 25 instruments on board, and we operate all 100 of those instruments. So we gather all the requirements from the scientists and command those instruments to do what the scientists ask for. It was a huge step for us to be able to operate those 100 instruments. And MMS itself, the mission, is well over $1 billion. We have other missions. If you follow us 2 weeks ago now, Cassini went into Saturn, finished the mission. It was a great mission. We had an instrument on there that studied the atmosphere of Saturn, looked especially at the auroras that Saturn has, and did a great job. And another neat thing about that one, it saw the plumes coming out of Enceladus, a moon out of Saturn, that actually contain water. And we went to Pluto, and we're operating a spacecraft called MAVEN going around Mars right now. We're doing the science operations for that. You kind of wonder, okay, so we've got 4 missions. We're in development for several others that are going to be operated from here. How do we do that, especially in the university? You know, you can think of NASA, you can think of the Air Force or the military operating this with very highly trained, skilled personnel. But how do you take a undergraduate and make them a spacecraft operator? First of all, these missions are, again, we take this very seriously. These are very expensive missions. We pretty much assign a full-time person to be the king of the mission, if you will, the flight director. Whatever he says, she says, that's where it goes. We go through a security training. We're pretty much just like a NASA person. We have a NASA background, a security check. We go through training, certification. One of the neat things about LASP is our folks pretty much get assigned to a mission when it's in development. So they see this satellite being built, and they're working with the engineers, and they bring to the table the lessons learned out of years of operating spacecraft. You know, what not to do, how not to design something because we have trouble with it. And then we take these procedures, and we have lots of years of experience on operating, and we know how to do it. We have all the stuff needed to be secure with closed rooms, with secure protocols, working with NASA. They review us to make sure that we're staying secure. So again, we look just like a NASA center. And we have some incredible software that we use on all our missions that is actually licensed, and Ball is one of our big customers for that. The students. So one of the really interesting things is we have students that work all over LASP. We have students that work in science, and they're working towards their master's or PhD, and they're doing this for their degree. In engineering and in mission ops and data systems, they're doing it for pay. It's a little bit different model, and it's actually we kind of own them for 20 weeks out of the week, 20 hours out of the week, and 40 in the summer, and it's a job. So they get paid, and they get paid less than professionals. So right now I've got about 120 or so people in mission ops and data systems, and about 60 of them are students, undergrads and grads. So it's financially, for NASA, it's a great deal. If you can imagine, we don't pay the students benefits, and the salary is a little bit lower than professionals, but if half your staff and you're getting the work out of them are students, it's a great deal. So we work them hard. They're trained in all sorts of aspects of how to operate a spacecraft, doing development, understand flight dynamics, how you plan and schedule events on the spacecraft, sending the commands, and then a really important job that they do is the health of instruments and aspects of the spacecraft. So we get telemetry down, we get data down from these spacecraft that tell you how the batteries are doing. And we sit there and we analyze it, and we look for trends, and we work with the vendor that provided that battery or the spacecraft and kind of work with them, and the students do that, and they do that analysis and help us keep the spacecraft healthy. We hire them at the end of their sophomore year, so they have somewhat of an experience at the university. It's a big jump from high school to college, and we kind of like them to have a little bit time under their belt, get a few courses through their freshman year, and we start looking at them kind of in January of their sophomore year. We hire, at least on the ops side, about 10, and start working them in the summer for training. They come from different majors, and it's always interesting. We will take, if you want to do ops here, we'll take any major, as long as you're really interested in learning how to do spacecraft ops. We teach you the basics from orbits to the software that we use. There's some skills that you probably need to have that we can develop here if you're willing to put the time into it. But it's not easy. It's not easy. So we do have many different majors, but most of them are science or engineering or computer science. Once they pass and they graduate from our training program, we assign them subsystems. So if you're interested in thermal, or if you're interested in batteries or whatever, we try to team you into those groups and have you do the analysis of those components. So that's pretty much how we do the students here. It's a great experience when you think about that they're actually flying real spacecraft. So I've worked with lots of companies around here, the Raytheon, Northrop Grumman, Lockheed Martin, Ball, Aerospace, and they all build spacecraft. Several of them operate spacecraft. Digital Globe has spacecraft. If you have Dish TV, they do. EchoStar has spacecraft. These companies are dying to have our students work for their companies, and it's scary how easy it is to get a student a job, basically. If you went through our program, they're very anxious to get you. In fact, tonight, the Jet Propulsion Lab is doing a program on campus for the aerospace engineering students. Their main recruiter was here at 9 o'clock this morning, already telling me which students she wants who are graduating in May of 18. And this is before she's interviewed them. She knows they work at LASP. And we have so many students that, the downside is there are so many students that love to go to JPL. Who wouldn't work on a Cassini or the next Mars rover? So there's we call it LASP West because they're in Pasadena. There's so many LASP students working there. So it's kind of cool. But I do try to spread the wealth around a little bit, so not everybody goes to JPL. A little bit about Kepler. So if you're not familiar with Kepler, it's the mission that was looking for habitable Earth-sized planets. And I'll talk more about how they did that. But it's been an incredible science mission. A little bit how it's done. Here's your sun. So you've got a little planet going in front of it, and you're staring at that, and the brightness. If you could see this, the brightness of that star dims, and this is over several hours, and then gets back up, and it's like a small fly on a bulb. This is an actual one of Venus going across the sun in 2012, and this is what it looked like close up. So what Kepler does, it's trying to look at the change in the amount of light coming from a star due to a planet going in front of it. So if you were at some distance from our sun and you had Jupiter going across the planet, this is what Jupiter would look like. Kind of big, pretty bright, or pretty much you would notice it. Can you see Earth? It's that little speck right there. If I could hold the laser steady. Probably can't see it in the back, but very dim, very small, very difficult to detect. So we built something that has a huge photometer, something that measures light, 96 million pixels. Kepler was, the lead scientist for Kepler was Bill Barucki, and his original paper was published like in 1980, 1981. And he went to bat for this mission over and over again. I'm not sure, like 4 or 5 times before the proposal was finally accepted. And he finally got the mission approved to go do this. We launched in 2009. LASP was on contract. We started a few times, but basically since 2006, we started working on this for 3 years. We developed everything we needed to do to get ready for Kepler. And launched on a Delta II, March 6, 2009. When we had this event here, we had an open house. It was an evening launch, and we had something like 400 people here. And they were all, we had the launch video on the TV, and then our operators were in the control room, and we had people pretty much looking at the glass, watching these guys. It was a little nerve-wracking, but it was fun. So to do that, you put Kepler in something called an Earth trailing orbit. Fairly unusual. It's going around the sun just like the Earth is, except it's behind the Earth. And we did this mission from 2009 to 2013. And the idea was you didn't want the Earth to get in the way. If you had a low Earth orbit mission, the Earth or the Moon would get in the way all the time. We wanted to be able to stare continuously at a chunk of space in our galaxy at those stars, specific stars. And so the scientist looked at this region of our galaxy. This is Cygnus and Lyra, so 2 constellations that are very bright in our Milky Way, but they didn't want to get in the Milky Way because there's so many bright stars, so many things to look at. So they kind of picked a field of view that was a little bit on the edge of an arm of our Milky Way, and then a little bit out farther. In this box, and you can see the original field of view of stars that's hanging up on a poster out there, that has 2 million stars, all within our galaxy, that is in that field of view. And Kepler, with these scientists for years, they've tried to figure out which stars to really look at. They picked out 150,000 stars to stare at for this life of Kepler. And the idea was, I'm going to look for planets going around those specific stars because they were somewhat similar to our sun. So basically what you're doing is taking light hitting pixels on this photometer, and how much light's coming in, and then you have what they call a light curve. So once that planet starts going in front of the star, in front of the star, it dips. And you can see that dip, and then it goes back up. The scientists wanted three data points from Kepler, and then they wanted a ground-based telescope to look at that same star and look at it and confirm that it really was a planet going across. What they found was a lot of these stars are noisy in the sense that, our sun has sunspots. Our sun sends out coronal mass ejections. They found that the stars are actually have more of these events than our sun does, which for Kepler is noise. It's background noise that they have to try to figure out that's not a planet. So they had to do more analysis. But anyways, Kepler 10b, this is kind of what it looks like. This is a really cool chart. In the past, we didn't know for sure. When Star Trek was going on, the original Star Trek, we didn't know there were planets going around other stars. We started looking at this in 1989. We found our first planet going around a star. We had several different methods, and I won't cover all these different methods, but in '89, it was one. Then we started figuring out different ways to find these planets, and we found from '95 to 2009, quite a few, a lot of large ones that are larger than Jupiter, Saturn size. Very small, very difficult to find ones that are the size of Earth. Now you throw Kepler in there. That's Kepler. The yellow is Kepler, so it blew them away. The number of planets that we found far exceeded what they expected. And you can extrapolate how many planets on the average out there. So Kepler only looked at these 150,000 stars. Our Milky Way is 100 billion stars. With the number of planets that they found, on the average, what I keep hearing is just about every star on the average that you see in the night sky has at least one planet going around it. If you look for Earth-like planets, and I'll show you some examples, it's about every 10 stars may have an Earth-sized planet. So that's pretty cool. And it's some amazing planets that are, you think of our solar system, the closest planet to our sun is Mercury, has an orbit of 90 days, 85 days, something like that, 88 days. They're finding planets going around stars in days. How can that happen? This is the latest from June of this year. So they're still analyzing Kepler data. They're still trying to squeeze out how many planets are still up there. We have a lot of candidates that have to be confirmed still, but there's a lot. 4,000. What kind of planets did we find? Anybody know what this is? Star Wars. 2 suns, 1 planet. We found that. We got an example of that with Kepler. We looked in star clusters. We found planets going around stars and star clusters. If you ever looked at a star cluster in a telescope, lots of stars. I think some of these, they would say you could, if you're on the planet, you could still see tons of stars even in the day. So depending on the brightness of the star. We found stars smaller than Mercury. So we've got all these examples. Here's Earth and much smaller planets than Mercury and about the size of the moon. So very small planets now that we can find. Ancient ones. So age of the universe. It's a little bit older than this, but this is one of the earliest planets that we've ever found that's close to the age of our galaxy. And there's all these planets that are, have a period going around a sun that's less than 10 days. So how fast would you age in a planet like that? It's pretty old. But yeah, so this is our solar system. These are different solar systems that we've detected with Kepler, all the way down to 444, bunch of small ones with very short, very small, very close to their star. So the habitable zone. We found now several planets that are considered in that habitable zone. And I want to show you kind of, so let's see, with the habitable zone, we kind of call it the Goldilocks zone, the area where it's not too hot, not too cold. So for Earth, we're in the right spot. We have, our sun keeps us warm, still some cold spots, but we have life here. If we were Mars may have had some kind of life, and so it's on the border of habitable, still too far away from the sun. Venus has some other effects going on that's too close to the sun. Earth is about right. So when we're looking for habitable zone, we're kind of looking for planets that receive about as much light, heat from that star as we do. And these are some of the ones that we've found. Yeah, 186F. So 186F is the one that we found is actually Earth size and in the habitable zone. This is a really interesting solar system. So F is the farthest one away from the sun. There's a bunch of other planets that they found that have much shorter periods, 4 days, 7, 13, 22. And this one is 130, mainly because the star is dimmer than our sun. And that's why it's considered in the habitable zone. It's closer in. So we also talk about a fireplace. So if you want to be, not too hot, not too cold from a small fire, you get closer. If it's a bonfire, you get farther back. This one, you want it to get closer. This is the artist concept of what it looks like. I'll let that play a little bit. Some very cool graphics. That's your 186F going out there. That's the star and the other planets going around it. Obviously, we don't know what it looks like. We think it could look like this. It's a cool picture, but the photometer doesn't tell you what the atmosphere is like or much about the composition of that planet, besides they can tell if it's rocky or not. And then you got your little planets going around in the back. But it's cool. Okay, so habitable zone. So M dwarf stars, type of stars. So the hotter stars, the habitable zone is farther away. Sun-like, this is our solar system. And then cooler, obviously that green zone is going to be much closer to the star. And that's what we found with 186F. Pretty close to Earth size. But if you look at their solar system, it would fit within pretty much the, close to the orbit of Mercury. So very different than what we have here on with our system. Again, different types of stars. Smaller stars that are dimmer, you got to be closer. Nice advantage of the smaller stars is if the orbit is shorter, you'll see it more often and easier to confirm that it's really a planet. So 7 out of 10 are dwarf stars. So our nearest one is a dwarf, and looking at dwarf stars is something we're trying to do. Habitable zone, something to talk about too a little bit is just because it's in the zone doesn't mean it's habitable. And there was some interesting stuff being done. Star's gravity. If the star grabs you like the Earth has grabbed the moon and you're only facing one side, that's not too good for life. We have the advantage of having an ozone, which protects us from extreme ultraviolet. If you didn't have an ozone, it wouldn't be too fun here. If you have a lot of flare activity, that could be a stopper for developing life. And if you had a lot of high-speed impacts where you lose your atmosphere, or if you're something like Mars, where it's losing its atmosphere, it's lost a lot of its water. So just because it's in that habitable zone, there's some other features that would prevent it from establishing life on it, but something else to think about. 452, really close to our sun. That star is 10% larger. We found a planet that was, close to being 1.6 times the size of the Earth and an orbit of 385 days. So 452b. And so this made the news, and I forget which microbrewery did it, but I think it was somebody in Louisville came out with a beer that was called 452b, Kepler 452b. And it was actually awful. I tried drinking it, and it was really bad. I couldn't tell I didn't want to tell the brewmaster that it was bad, but it had some weird chemicals in there. Kind of wonder. So 452b is there, close to Earth, and these are different types of planets with different stars. But even 452 is, 1,400 light years. New Horizons that was launched, that went to Pluto. That was one of the fastest rockets we ever launched. It was on an Atlas V, and it was a small payload. And if you think back to Apollo, it took Apollo astronauts about 8 days to get to the moon. No, 3 days to get to the moon. It took New Horizons 8 hours to get to the orbit of the moon, so it was hauling. And it still would take you 26 million years to get there. So quite a while. Kepler only looked at a small slice of our Milky Way. So this little slice, 3,000 light years. So we only looked at a little bit of it. So again, we're extrapolating from that chunk of data that we collected. Lots of other missions coming up. I'm going to talk in a minute about K2. James Webb, if you saw that's had some challenges technically and little overruns. It's now a $8.8 billion telescope, and it's going to get launched now. They slipped it to June of 2019. So it was October 18. But anyways, I'm not aware of any other $8.8 billion systems that we put into a rocket. But it will look for planets too. So one of the cool things, so Kepler had some issues. We normally operate with 4 reaction wheels. 2 of them failed fairly close together. The reaction wheels are used to stabilize the spacecraft and point it very accurately so that when you take your photometer that has pixels in it, you can pretty much put a pixel on a star and hold it there for days, months, and collect that data. And without these 2 reaction wheels, there were, the media basically said, it's a dead mission. We can't do anything with it. So in 2013, there were stories that this was the end of this mission. So what did we do? We had some bright engineer, and maybe a couple engineers, but one in particular at Ball, that used something called solar pressure. Now I'm going to talk about that. It changed the way we had to do the mission. We were able to stabilize the spacecraft for a shorter period of time, but we were still able to do science with it, and we completely changed the science that we did with Kepler due to these anomalies, but we're still doing some really cool science that was not planned at all when we established the mission. So a little bit about solar pressure. So the sun puts out particles, photons, high-energy particles. It's called pressure. If you were, the amount of pressure that I understand it puts out is a piece of paper, the amount of pressure a piece of paper would have on a table. Very little. But you can use it to stabilize a spacecraft in one axis. And we still have 2 good reaction wheels, so we can stabilize it in 3 axis. Just what you need to still stare at a spot in space. And we can do that basically for 83 days at a time before we have to rotate it again. So what do? We changed the science. We said, okay, we're going to look at areas along the ecliptic, and so basically your zodiac constellations. We're looking at a field of view that is 100 square degrees. So pretty much the palm of your hand up in space. That's the size of the field of view that you're looking at. If you think about Hubble, so the Hubble Space Telescope is looking at a field of view also. Its field of view is, if you hold up a penny and you look at Lincoln's eye, that's the size of the field of view of Hubble. It gets really cool pictures, but it's not doing the same science that K2 is doing. So we're looking at comets. We looked at Siding Spring. We looked at a young star cluster. We looked at stars forming. There was tons of science that we started doing, and we do this by asking the science community, here's a section of space we're going to look at. What's cool? What science can you do in this chunk of space? Looking at this chunk of space. This is the stuff they came up with. It's very diverse. We're still doing exoplanets. We're still looking for planets going around, but we're doing, looking at white dwarfs. We're looking at eclipsing binaries. We're looking at galaxies. We're looking at supernova. It's just amazing, all the stuff you can do. Basically looking at anything in that field of view from zero magnitude to magnitude 22, so to very, very dim. And it's just all over. These are slices, so it's just amazing the things that the scientists have come up with that can be done with this mission that people thought was going to be dead. Creative scientist is an artist also. Kind of came up with this paper napkin diagram of the mission that we're currently in, 15. So in this field of view, we're looking at brown dwarfs. We're looking at a system that has a white dwarf chewing up a brown dwarf star. We're looking at a globular cluster. We're looking at supernova, comets, everything that's in that field of view. This is the kind of science that we're doing right now, collecting. Just as an example of some again, science that is changing the textbooks. There's supernovas that occur very infrequently, but they're very spectacular. We typically get those and to tell you the truth, most of the time it's amateur astronomers looking out there that will pick up something going on. There's a lot of amateurs that have nice telescopes that do astrophotography, and they'll pick galaxies out and they'll take images and then they repeat it and then they look for supernova and let other folks know, and people point their ground-based telescopes at it. But it's usually after the event. Here we had an event at a galaxy that was a supernova, and so we usually think these are events that take place over several days, like 18 to 20 days. We found this nova, this star, exploding over 18 hours. So very, very, very fast. And the only reason we could do that is because K2 was staring at that star, at that galaxy, and picked it up. We have theories about why supernova take 18 days. We don't have any theories about how it could happen in 18 hours. So 10 times faster than we've ever seen before. And we've got 15 supernova that we're looking at. So pretty much the idea of the reason I like to tie K2 and Kepler and students involved is, and operations, because I love operations, is the idea that spacecraft, when stuff happens on spacecraft that are totally unexpected, that's when the fun begins for ops. That's when we start being creative and we come up with things that have never been thought of before, and we do new things and we keep the mission going. NASA loves it. Unfortunately, Kepler is going to run out of fuel sometime in 2018, late 2018, and that will be the end of mission. unless somebody can think of ways we can use it without fuel, but that might be exaggerating a little bit. But anyway, so we found, so far 44, almost 4,500 candidates, 2,300 confirmed planets. K2 has found a whole bunch of candidates and more confirmed planets, and all this new science that was never done before. And there's tons of papers being published on the K2 mission. So I saw some numbers last week that showed majority of these papers are being published by scientists that have less than 10 years since their PhD. So new scientists, new astronomers are getting involved in this science. So it's very fun to see that being done. And with that, I'd like to show you what we're working on next here at LASP. And nobody knows this, but we're building it in another building here. And we're getting ready to go out to those planets now. So anyways, with that, I'd like to thank you. And if you have any questions, happy to answer any questions. Yes?
If the science of Kepler changed with K2, how did your operations team change to meet those new science?
Right. So we had to change the cadence of our ops. So we changed a lot of procedures. We changed how we staff. We have to staff at different times now, and so it was some work to get going with it. But yeah, we basically just changed how we operated it. Different staffing profile.
Do you have enough resolution to determine the angle that the planets are?
That's a good, yeah, so they're pretty much parallel. I mean, they're pretty much horizontal. So, there could be a lot of stars that we were looking at that we couldn't tell because of the angle that they were planets. Yeah.
What about this rotation, though? If it could be.
Yeah. So I think that, yes, right. They could see that.
Okay.
Yeah. Yes.
What's the male-female ratio of your students that come in and work here?
I think we're 30% are female.
Because then engineering isn't going to try to get the 50%?
Yes, they're trying to go higher. We can only hire CU students, so whatever CU brings in, we can hire. And so we're limited in that way by that. But it's fairly consistent with what CU brings in.
Bill,
Yeah.
What is the numbering system? I noticed that there's numbers and then there's letters afterwards.
Right. So I believe, and you guys can correct me, 444 is the 444 planet system that we found, and then A through whatever is the number of planets. So A is the closest one to the star. Is that correct?
Yes.
Okay. Yep.
Can you just expand on what you mean by Kepler's going to run out of fuel?
So Kepler has still has the reaction wheels and has thrusters that we use, and those thrusters use hydrazine fuel, and we're getting to the end of that amount of hydrazine that we've had. So once it's out, we can't control the pointing of the spacecraft anymore. Yeah.
Is Kepler able to determine whether or not planets are gas planets or rocky planets?
I think there's a kind of a interesting stuff that the scientists do to figure that out. I don't think it's not by direct observation, but they seem to have a way to figure that out. Yeah.
What kind of control mechanism did the solar pressure lend you such that you had a third axis that you used to control?
It's pressure. It's just keeping that axis balanced against the two reaction wheels. And then you have little thruster firings to keep it pointed in that direction. So it's not pointing as well as the original Kepler mission, but it's accurate enough for the science that we're doing.
So you can't point it in an arbitrary direction.
Right. Right, we kind of have to keep it along that ecliptic and based on the solar pressure. Yes?
So keeping it in that attitude where you're stabilizing it with the solar pressure, did that significantly cut into your fuel consumption?
Yes. Yeah. Yeah, it does. Yeah. And we're still, the engineers don't have an exact number of amount of fuel that we have. We have a good estimate, but we don't know exactly. So we don't know exactly when the end of the mission is going to be. We keep planning to have more, but they're really thinking sometime, last quarter of 18, we'll be out of fuel. We'll have some sort of celebration here, though, if you want to come back for that. Yes?
What's going to happen when it runs out of fuel? I'm assuming it's far enough away it's not going to deorbit.
Right.
Or is it?
No, it doesn't deorbit, and I know some of the folks were talking about when is it going to come back around to Earth? Like 60 years?
30 years, roughly.
30 years?
Before it actually gets anywhere close to us, and it's the orbit's designed to where the closest approach is 150 years later, and that's still a very long distance away.
Beyond the distance of the moon?
Yes, beyond the distance of the moon.
Okay. So that'd be cool. Go up and grab it and bring it back and put it in a museum. We should plan that for 150 years from now, okay?
If you pay for it.
Yep.
So how does a planet go from a candidate planet to a confirmed one?
They use the ground-based telescope. So they want to use a ground-based telescope to confirm it. Yeah. Okay, again, thank you very much.